This is a continuation of previous lecture, lecture 10. Sometime you can look at residuals to see where the model does not fit well. For binary response, we define Pearson residual, and this is YGI minus pi GI hat whole square root over pi GI hat plus minus, and we see that this is simply as yi minus pi I hat by root over pi I hat 1 minus pi I hat, and we denote this Ri. In large sample, we can replace pi I hat by pi I. Now expectation Ri approximately 0 and variance of Ri approximately 1. If the true model expectation yi equal to pi I star not equal to pi I, then expectation Ri not equal to 0 and variance of Ri not equal to 1. Thus, if we look at the simple average of this residual, one by n sum over I from 1 to small n Ri, and do not get around 0. It gives us an idea that the model does not fit well. And if we just look at the average of the squared residual, that is 1 by n sum over I from 1 to small n r I square, and we do not get around 1, then we know that something may be wrong with the model. If the model fits then variance of Ri approximately equal to expectation Ri square approximately equal to 1. However, since yi is always 0 or 1 regardless of the sample size, since yi is a Bernoulli and does not change with sample size, the observed residuals is not really the informative when the data are binary. Note, the ordinary residual yi minus pi I hat are not, which I defined simple residuals in our previous lecture, lecture 10, are not as informative, since you can show sum over I from 1 to n yi pi I hat equal to 0 as long as there is an intercept in the model. Suppose the data actually arise as I binomials, that is the whole observation divided into I groups, where yi is the number of successes and ni the sample size of ith group. Then pi I hat equal to e to the power beta curl prime xi curl by 1 plus e to the power beta curl prime xi curl. Then the Pearsonian residual Pearson's residual equal to Ri yi minus ni pi I hat by root over ni pi I hat 1 minus pi I hat. For large sample case, it is Ri yi ni pi I root over ni pi I 1 minus pi I. If the model is correctly specified in large sample, this residual will have mean 0, that is expectation Ri approximately 0 and variance of Ri approximately 1. Note that also yi when ni is large will become more normal as ni is large, and in that situation Ri follows standard normal. Then if the model fits, we would expect that the 95% of the residuals to be between -2 and +2, and to be approximately normal when plotted. If the true model expectation yi is equal to ni pi I star not equal to ni pi I, then expectation ri not equal to 0 and variance of ri not equal to 1. Still yi will becomes more normal as ni gets large, but here ri follow normal with mean expectation ri. I denote it mu I say, and variance of ri I denote it sigma square I say. Where mu I equal to expectation ri, this is nothing but a ni pi I star minus ni pi I by root over ni pi I 1 minus pi I, and sigma I square is equal to ni pi I star 1 minus pi I star by ni pi I 1 minus pi I. And since summation ri square follow chi square with p degrees of freedom, then I already defined p in my previous lecture. Please follow our previous lecture for definition of p, and then this imply expectation sum over ri square divided by small n, that is total number of observations, which is equal to p by small n less than 1. The standardized Pearson residual is slightly larger in absolute value. So now I define Pearson residuals, because since expectation ri square by n is less than 1, so we define standardized Pearson residual because this is slightly larger in absolute sense. So before defining standardized Pearson residual, first I define hat matrix. So I recall this is a dispersion of beta curl hat asymptotic variance W hat, where W hat is a diagonal of pi 1 hat 1 minus pi 1 hat pi n hat into 1 minus pi n hat, and x is n cross k plus 1. Since we take k explanatory variables and first column of X matrix is whose all elements is 1, and these are k covariate or explanatory variables. So here hat matrix denoted by capital H, which is equal to W hat whole to the power half x x prime W hat x inverse x prime W hat whole to the power half. This is same as weighted least square of linear multiple regression model, and I denote this H hat, and Hi hat equal to estimated diagonal element of H hat for ith observation. Then as the same way as defined in multiple linear regression model, that is a student type residual, here we define standardized Pearson residual Ri star instead of Ri is equal to Ri is a Pearson residual divided by 1 minus Hi hat. This is the same structure as student type residual for multiple linear regression. Now, if this absolute value values larger than roughly 2 or 3 depending your choice, provide evidence of lack of fit. Now, this hat matrix H, W hat to the power half x, x prime W hat x whole to the power minus 1, x prime W hat to the power half. In linear model, the hat matrix is so named because H hat into Y curl projects the data to the fitted value mu hat. For GLM, applying the estimated hat matrix to a linearized approximation for G Y curl yields eta hat equal to G mu curl hat. The model's estimated linear predictor values. The greater an observation's leverage, the greater its potential influence on the fit. As in ordinary regression, the leverages fall between 0 and 1 and sum to the number of model parameters. So the leverages as in ordinary regression, the leverages falls between 0 and 1 and sum to the number of model parameters. Unlikely ordinary regression, the hat values depend on the fit as well as the model matrix, and points that have extreme predictor values need not have high leverage. Now, plots of residual against explanatory variables or linear predictor values may detect a type of lack of fit. So plots of residuals against explanatory variable or linear predictor values may detect a type of lack of fit. When fitted values are very small, just as chi square and capital G square, lose relevance, so do residuals. When explanatory variables are continuous, that is ni equal to 1 at each setting, then yi can equal only 0 or 1 and ei can assume only two values. One must then be cautious about regarding either outcome as extreme, and a single residual is usually uninformative. Then plots of residuals also have limited use, consisting simply of two parallel lines of dots. The deviance itself is then completely uninformative. When data can be grouped into sets of observations having common predictor values, it is better to compute residuals for the group data than for individual subjects. Before ending this lecture 11, I recall deviance residuals. So the deviance residuals for ith observations, which I already discussed in lecture 10, that is equal to root over di sine of yi minus ni pi I hat. That is, this is plus 1 when yi minus ni pi I hat greater than 0 and minus 1 when this is less than 0. And di is 2 into yi log yi ni pi I hat plus ni minus yi log ni minus yi ni minus ni pi I hat. And this is also tends to normal 0 1. So you consider these deviance residuals also. So please stay with us. We will continue logistic regression residual diagnostics in our next lecture. Thank you.